All right, good afternoon or evening, everyone. Monday, October 20th, just for everyone here as well, and for those watching the recording. Geostats class, it's been a while since we officially met because we had fall break last week. We had the midterm the week before, and then we had the review before that. So we've got the next 6 weeks of class that we're going to kind of power through, and that includes the very last day of classes. We're going to talk about circumventing issues in GIS. So for the rest of the class, we're largely going to talk about a little bit of correlation, but inferential statistics, and those begin today when we start talking about that normal distribution, z-scores, and all these things here. My major focus is when we run these tools, how do we interpret these? I'm not going to focus too much on the math. You can see over here, I got a couple formulas I'm going to bust out here. But at the end of the day, I want us to focus on the GIS skills, the GIS techniques, so we can put in these big formulas because you're going to see like gamma notations, you're going to see these really E's and all these other things. But guess what? Excel already does this for us. And I've actually posted a template in Canvas already that has the formulas in there. We need to just run the GIS analysis so we can look at something called the Poisson distribution, which is a type of random distribution that isn't going to be, that's not going to be focused around a mean. It's going to be it's going to have a little bit of a tail to it a little bit more. Last week I posted some announcements. Midterm is graded. I kind of had mixed feelings about the midterm. It looked good, but you kind of had a couple of the haves and a couple of the have-nots. So make sure you're able to open this stuff up, able to do it, have it ready to go with all the spatial joins and whatever. And so most people had it ready to go, but I had people like, what's the password? Password's the password that I posted it. You know what I mean? I can't open up the project up the week before. Or those of you joining it now or later, reviewing it now later, follow my little tutorial and open it now and call me or call Chima. How do we open up the project before we, while you're sitting there wasting the time to go through and do that? Some of the content's pretty tough. It's tough. You got to relearn some things. What makes a good z-score, all that other good stuff. So I think a lot of people hamstrung themselves kind of with some of the tech stuff that we kind of talked about. Some people just opened it up, had the project ready to go, and it's hard enough doing the exam as it is, and having to worry about some of that tech stuff. So I was happy about the folks who were prepared because it's tough. This is graduate level geostatistics. We're covering statistics and everything else. Second thing, make sure you have the exercises, Esri tutorials, everything else kind of done. Oftentimes I get questions like, and sometimes not very nice, like you haven't graded exercise number 1. I don't even know if there's a question in there, but you haven't graded exercise number 1. I'm like, we're at exercise 4. Like I'll get to exercise 1 when I get to exercise 1, just because you don't know what your grade is right now because you turned it in 3 weeks late isn't my concern there. So I'll go through and grade the things and make sure they're, if they're late, they'll get half credit and all that other good stuff. But moving forward, I really want stuff that kind of be turned in on time, and we'll see a penalty incurred with this because I know learning curve is really steep with people learning GIS the first time. So I do want to give a lot of grace, but I don't want that grace to be taken advantage of by folks who, should have it ready to go. Like I said, no class last week. And we're going to look at the position paper as well. I'll kind of step back and look at that in a second here, because the position paper to me is like the beginning of your master's project or your thesis or a project that we have here. And I'm going to show a couple of papers that people taking this class did that I really like. They're really good. They answer really simple questions using what? Some of the statistics that we're going to talk about a little bit this week, but more so next week when we look at something called two-tailed t-stats. And people nodding their head in there because we've heard of these before in statistics. When we make statements, we go through and try to prove or disprove those, and we typically use those using inferential statistics. Same thing we do with these cluster maps. You start to see some of these red maps and blue maps with the hot spots and the cold spots. And all those are just inferential statistics that tell us what are the chances those high values around other high values when we compare it to a random distribution where some highs are near highs, lows are near lows. Okay, and to me, the trick with those is, and we'll talk about those in a few weeks, how do we adequately word those in a paper? Because typically I just run an Excel, I pop it into Excel, I'll pop it into ArcGIS Pro, I run it and it gives me numbers and I just say what it, say what it means. So a lot of hand jamming and calculations we're not gonna kind of work, we're not gonna discuss, but there's a lot of input parameters that we have as well. North Carolina State Internship Program is up there. Also, some jobs I posted. I have a daughter who's entering the workforce and kind of tells me there's no jobs, there's no jobs, there's no jobs. And guess what? Job, 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 job. It's not exactly where she wants. Okay, darn, you're going to have to go live in,
Need something, you're gonna get something else.
Yeah. You're going to have to go and, you're going to have to go and maybe live somewhere you don't want to live. Maybe live in Columbus, Ohio, or whatever. I'm not sure what what it is here, but it also, there's a lot of competition for these here. I just posted this one up here that I liked. This is with the state of North Carolina. This is Engineering Tech 3. I'm a big fan of the NCDOT, the photogrammetry unit. Photogrammetry is a big fancy word for using imagery, satellite, aerial photography, drone imagery these days to do real world measurements related to transportation planning, design, and construction. We have two former students who work in the photogrammetry unit. A guy named Ben, a guy named Nelson. Nelson's been there probably 8 or 9 years. He came to our last GIS day. I'm a big fan of Nelson. I see him around sometimes, and hopefully he'll be able to make it for GIS day. Benjamin just started, and then we had another student named Roderick who worked there a few years after working utilities, and then he transitioned over into utilities mapping over at the NCDOT. You provide Engineering Tech 3 advanced level support for the planning and production of photogrammetric mapping for functional design, preliminary design, final design, digital map plotting, image processing, skills in GIS, LiDAR, photogrammetry, GIS, location design, construction. Because a lot of times when you go and get a quote unquote GIS job, you're not like, we give you everything. We give you crime, we give you transportation, we give you history, we give you everything. When I worked with the military, we were mainly focused on general mapping so that the military could train in environmentally, fiscally, and socially responsible manner. So where are the roads, where are the endangered species, where are the training areas, where are the exact training areas, so you can go and create those using a GPS unit. And so, when we go in GIS, we're kind of throwing everything, the baby bathwater, kitchen sinks at everyone here, but these are relatively specialized. So at some point in time, when you come back to present at GIS day, you're going to be a lot better than me at this GIS stuff, especially focused on transportation or photogrammetry. I'm a big fan of this. This Engineering Tech 3 is up now, but I would assume that they're probably going to promote someone from within. So an Engineering Tech 1 or 2 will be open. But you can see the pay range for these go from about 44,000. This is probably starting all the way up to about 76,000 just for this pay range. And then you go from an engineering tech, you go to an engineering specialist, and then you kind of turn into the boss there. I know him, he's a really good guy, guy named Richard. And then his assistant is now head of the NCDOT drone unit, UAS unit, guy named Nick. And so he's hired students for internships before. We've had a number of students do HBCU specific internships, fellowships, lots of great things there. I'm always a big fan of the NCDOT and the work they do. They've been big proponents of us, big proponents of me personally, and they've funded a number of grants and students that have come through our department, and I hope they can fund some more in the future. So I like that. So next, in course modules, you'll see down towards the bottom, we have week 14, we got the final examination. Okay, we've got the position paper, and then I got tons and tons of external links. But this position paper is basically, you're going to make a statement and prove or disprove it. A lot of times when we make these statements, and we see these statements all the time that come up on our, come up on our phones, and are they, are they proven? Are they disproven? Are they do whatever here? Because a lot of times when we do stuff in class, we're just mapping stuff, mapping ulcerative colitis, we're mapping SIDS, we're mapping ADHD, we're mapping, I can see that one in the back that's really faded. We're mapping birth defects. Okay, that's all good and well, but from those we can make concrete hypotheses about, hey, rural areas have a higher infant mortality rates, or I think those are birth defects, than urban areas. That's that back one in the purple there. That back, that feed one in the purple there. Okay, so we can start to make real direct statements about those. Why? Well, access to healthcare, all these other things here. And so what I ask people to do is take a position, or it could be a really small or basic position, and prove or disprove it, doing a combination of what we call loosely coupled data or even tightly coupled application, where we could do this all in ArcGIS Pro. And in some cases, hey, let's just go and prepare some data and do some hot spots and cold spots, because basically you're running geostatistics on those data. The proving and disproving thing gets a little bit more difficult, but we're going to talk about that next week when we prepare data so we can run some real simple two-tailed t-tests.
Sure.
I love two-tailed t-tests. You know why? Because I'm good at those. And maybe 10 years ago, I wrote a paper and someone said, why don't you do the two-tailed t-test? I was like, I can do this. I can generate this in a GIS, export these out. And some nice probability distributions, and all Excel gives me is just a little thing there that says true or false. And that's what we're going to be looking at today. They're going to give us a p-value that's extracted from a z-score. And we should all know what a z-score is. That's that standard deviation, which typically range in most data from like -3 to +3. So those are on the ends right there versus everyone else, which is in the middle for a typical normal distribution. I've got a couple papers right here that students have done. These are in the past couple semesters, but these are just papers that were done in class here. Did you do this one, Sheila? I'm not sure if this one was yours. But this is a spatial analysis of COVID-19. Yeah, this is Chima's. Okay, Chima's star of the show here.
All right.
Yes. Okay, but this is a spatial analysis of COVID-19 variation between urban and rural counties in North Carolina. Is there a difference between COVID-19 incidence rates? And he actually looked at death rates between urban and rural counties. Now, big question is, what's rural mean? Do you remember how you defined rural and urban?
We use the root car, we use the census, US census. So we kind of use the.
I like these maps here. I like these. So what's the urban, what's the rural? Okay, so first of all, and believe it or not, there's lots of different definitions of urban and rural. Okay, because a lot of times, how do we quantify it? I think for this one, it looks like you probably use MSA. Does that sound right?
Yes.
Okay, I don't even see up there.
Yeah.
MSA. Basically, MSA stands for Metropolitan Statistical Area. Okay, MSA, Metropolitan Statistical Area. These are county level designations that designate counties as either metropolitan, which have a high population, surrounded by other high population counties, micropolitan, which are kind of like Pitt County or this Onslow County there, and then, but I think they have at least a city with 10,000 people in it, because there's some weird things, and then everything else is rural. Because Elizabeth, the funny thing about this here is that Elizabeth City is up here. This is, what county is that in the corner? Not Camden County. This is Camden County up here, or Currituck County right here. And it's got like 10, it's only got about 20,000 people here, but Sampson County has 50,000 people, but they're all kind of spread out, and they don't have a city that's more than 10,000 people. So you run into all these issues there. We'll just leave it at that. So it's kind of interesting. It's kind of interesting here. So we got the urban and the rural, because your definition of urban and rural might be different. Chima alluded to something called RUCAs, rural urban commuting patterns or commuting areas, which these days are available at the census tract, zip code, county level. So where are people going from to go to work? So, if you're down here in Chatham County or Randolph County, where do these people go to work? They're not working there in Asheville. They're typically going, it's just a bedroom community there, bedroom community for some of these other counties, Okay. And so this might be different depending on the definition of rural. So the first thing he did was lay out rural. And all he did was he just went and found the COVID death rate. We're talking about rates here, the whole idea of normalization in everything that is yellow versus the death rates in purple. Is that right? Okay. It's a lot. I'm explaining a lot simpler than all the work that he put into it. So he had to put together like 3 years worth of work. We got dashboards, we're downloading things, and I explain it in a sentence. Probably doesn't do him enough justice. But when we look at this distribution of the stuff in yellow, it's just going to be a histogram. We're comparing two histograms, and if they kind of overlay with each other with the same means and medians and variances, guess what? There's really no difference between the stuff in yellow versus the measurements in purple. And that's basically what a two-tailed t-test does. Kind of, we can make assumptions like, hey, the average height of everyone at NCC was taller than the average height of everyone at A&T. Now, if you just did it for me versus someone over there, someone on the basketball team, well, I'm going to lose. But eventually we need to get enough of a sample size without me having to go and survey every single person at NCCU versus every single person at A&T, which would defeat the whole purpose of it. No, you surveyed everyone? Oh, I'm sorry. Yeah. We don't use that cue.
I know, but when I did my thesis, I did it
qualitative survey, qualitative data. Oh no, we don't want to do that.
I know, I don't want to do it again.
Well, Survey 123 does have good ways to express and visualize qualitative data. I'm not a big qualitative data analysis person. So what he did, you can see what he did here. So we just create a histogram of all the rates. It was like 2019, 2020, 2021, and we just computed these against each other. And these are the results that he had here. So you can see these were rates for 2020 versus median for the mean. So in urban areas it's 52.56. In rural areas is 51.69. Those are pretty close to each other. So me, without even having to look at the results of the two-tailed t-test, I could probably tell you those are going to be statistically the same. We phrase these differently. And so when you start getting people reviewing papers, it gets really nasty. Like it can't be proven that they are different. And I just like to say they're the same. But instead of, it can't be proven that they are statistically different or supporting the null hypothesis versus the alternative hypothesis. But we have these, what we call p-values here that are going to be converted from these t-stats, which are derived from z-scores. A lot of times with these t-stats, you can kind of substitute these for z-scores for the most part, and you can see they go from like 0 to 4. I think with your t-stats, they're not negative. So you can see the cases, we got 110 versus 105. You can see they're slightly different, but not quite. And then we can see in 2022, it's 149 in urban areas versus 126. And you kind of start thinking of that. If we were to sample 100 people at NCCU versus North Carolina A&T, and the people at NCCU were 6 inches taller, you're like, all right, maybe you got a case there for something. So it brings into account the variance of the data, how varied it is, which we know, as well as the sample size. Because if I just, if I just ask two people, that's you're gonna have a high margin of error. So, hey, if we get to a 6-inch difference, we're starting to reinforce this hypothesis. And so you can see with the cases that this is the rate here, 149 versus 126, you can see this p-value is really low. This means that there is a 0.000 or 0.003% chance that this difference can be attributed to randomness. Okay. Here, all right, they're different here. They're different, but probably they're not what we call statistically significant. Statistically significant is less than 0.1, 0.05, 0.01, 0.001. Saying, hey, here, this one, these death rates are 0.51 versus 0.41. They're pretty different, but not different enough for us to say they're statistically different. There's an 11% chance that, there's 11% chance that these could just be the result of me picking out a different crew here. This is a different batch or different sample. And so that's not strong enough for us to say these are statistically different. Here it's 0.58 versus 0.55. So I like this here because I don't want to use the word simple, but a lot of data development went into this, but we utilize the skills that we have in class.
The question while we're on this slide or so on that one for cases, the 2022, and where it's highlighted, we can see that statistical difference. Right next to it for the column furthest to the right, it's showing 1.99, and the rest of them are all like about 1.9.
Yes. Let's Chima, can you explain this for us?
Because to me it doesn't look like a big difference, but we know that in that row we have a statistical difference. At least
what this does, the critical value means this z-score needs to be, this t-value needs to be above this in order for it to be yellow here.
Oh,
yep. So
okay.
This, if any of these were above this number here, and this number just changes slightly based on your variance and your sample size.
Okay.
Now all the sample sizes are the same, so it's only going to be a function of this variance here.
Yes. So because the critical values are kind of thresholds that you want to see if the p-values go up or in kind of like cannot hit that statistical significance. So they don't really change as much as you see those numbers because it's just like a threshold.
Okay. Yeah, that makes sense.
And I don't want to call Chima out on the spot, but why do you submit this to something? Like clean it up a little and submit this.
Yeah, I
Like-
didn't know it was this good. We actually presented it at CDAC that same year.
Okay. Oh, I don't remember any of that stuff. So
They asked me to do the presentation. Yeah, it's like we presented this one.
but you can see the cases per thousand population. Remember, we talked about the idea of normalization, and I assume this is for 2019, 2021, 2022. You can start to see here in 2022, they start getting higher down here. It moves overall a little bit, and eventually they kind of, you can see the spatial patterns related to these. I always like the maps that Chima makes because he's got a lot of internal contrast here with the whites, the pinks, and all of these. He does a good job of making these maps and these visuals. And then when we look at the depths here as well, and then charts and titles here. Like this is, you can just easy to visualize. This is something my grandmother could look at. My kids could look at. And they say, hey, look, the blue is really high. Okay, what's the blue mean? Okay, population, poverty, vegetable spending, chart type, and all these others.
It was like the OLS regression where we're trying to.
Yeah, he was playing a little bit, looking at for explanatory factors. Is that right?
Yes.
Okay. And we'll talk about regression later. There's a whole lot of caveats to regression that I don't want to, you can do a whole thing on regression that I don't want to kind of get into here. Another thing, just related to COVID, this was by V, yeah. V is, I think she's adjunct in some classes this
Yes, she is.
semester. Former student, but she wanted to see if there was a difference in suicide rates throughout the state between 2019 and 2020 with COVID. Pretty simple to do. Once again, we got to we approach it from a spatial angle here. And so she did the same exact thing as Chima did, and I think he did it at the county level. And so what she did was she got two maps. She got a map of suicide rates for 2019. So we have a distribution of 100 deaths, just a nice normal distribution with the lowest and the highest. We did one for 2020. We made the same. And then how much did that normal distribution line up with each other? That's all she did. So where Chima was working with rural versus urban, so his sample sizes are actually going to be a little bit less. Lower sample sizes is not as good because you're just going to have higher margins of error. But now you can't really help that. You can't just magically make up urban rural areas unless we go down to the zip code level. And then at the zip code level, you're going to be running some wonky values with COVID. Like if you've got 5 people and 4 people had COVID, you're going to shoot up your COVID rates for these things. And we've run into those problems before. So V did a really nice job. I'm not sure but she did a lot of good explanations. She had, I'm not sure if this might be arcade, but you can see the calculations right here. She did field calculations. Hey, this is my field calculation to calculate the suicide rate. What she did was she downloaded all the data from the North Carolina Vital Statistics Database or North Carolina Violent Death Reporting System, which collects these at the county level. So I'm always big on the previous exercise that we had, we're largely focused on that vital statistics database. What you die of, counties, all this other stuff, but it looks like it kind of agglomerated these into the violent death reporting system. Probably has the number of suicides by county for 2019, number of suicides per county for 2020. And then what she did was she just went and calculated the suicide rate for 2019, calculated the suicide rate for 2020. And then it looks like she added some, changes and things like that. Some of the things I did like, you can see for 2019 to 2020, did it go up? Did it go down? Did it stay the same? And so you can see some of the changes right here. 46% experience changes, decrease, increases, no change. So I thought this was interesting here. These are good. I like these maps. But what I liked was we got variable 1, 2019, variable 2, 2020, went from 13.56 up to 14.4. That's a change. You can see this is your sample size. Why does it happen to be 100? There's 100 counties. Where that Chima might have been 50 and 50 or 55 and 45. And so these calculations, which we'll do next week, but we're going to look at p-values today, but run behind the background, it says it gives me, and I'm going to focus on the 2-tail, 1-tail just focuses on, hey, it increased one side of that tail. But I like focusing on the 2-tail because I like focusing on the 2-tail just because it's going to be a little bit more, it's going to be stricter. Okay. If I got the 1-tail, oh, look at the 1-tail, it's 0.09, but I want the 2-tail. So it was different, statistically different. Okay. I could say, it increased here, but what David was asking about was that critical. Okay. So this number needs to be above the critical in order for it to satisfy. And it is not quite there. And the p-value for the 1-tail t-test is there, 0.08. 1-tail, I'm saying, it increased between 2019 and 2020, because Here it could say, oh, well, it increased or it could have decreased. You know, so if this was 13.56 versus 12, okay, it went down. And so we've got a lot more leeway. We got a lot more, it's a lot more strict when we make these generalizations or make these hypotheses. But these are a couple of them that I really like that kind of, to me, hit the, kind of, really met the mark there. Now, what are different things that you can do here? And I've got the paper rubric, I've got the position paper, I've got a template right here. One of the things about this template, those of you paying attention right here, a lot of times I already have an interactive table of contents in here ready to go. Okay. So I got an interactive table of contents, so I can do view. So you see this highlighted in gray right here? Yep. So I've already put in all the headings. What do you put here? You put in a little abstract. 250 word abstract, introduction, lit review, methodology, conclusions and results. And so watch this. If you call this, I hit this down to the end here. Watch this. And then now I can go back here, right mouse click and do update field. Look what I just did. Conclusions and results, we're at page 3. So this thing's up and ready to go. So a lot of times when we do style guides for our projects, master's projects or master's thesis, just remember, hey, Mulrooney, you already created something that's got an interactive table of contents. I don't have to go back and type in the page. I've seen people go like dot, 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 hit the little dots. Man, Mulrooney, how did you do that? You're pretty smart. No, I did this once probably 10 years ago, and now I cut and paste this thing in here. And this is the difference between working harder and banging your head against the wall versus working smarter. Hey, I remember I already did something like this. Now, I probably couldn't tell you how to do it right now, but guess what? I got it sitting right here. Do I know how to change the text? No, but it went back to a different font, but I'm going to do a Control-A, change it to my Times New Roman, and it's going to be ready to go. Okay, but we've got, and so use this as the basis for your project. I get pretty passionate about these. These are the things that I want people to be, good at. I want you to be good writers, good presenters. This could be something you could present at GURBS. And it could be something really, really innocuous. Like, let's make a statement. But, motor vehicle thefts are higher around the NCCU campus versus the rest of the city. We got crime data for 2024 for motor vehicle thefts. Let's look at the let's look at the 15 census tracts around the NCCU campus versus the other 50 outside of campus. Let's compare those 15 rates versus the other 50 rates. Go from there. Okay. We could also use descriptive statistics as well, because I like this inferential statistics, the 2-tailed t-test, but hey, last year there were, 72 motor vehicle thefts within 1 mile. Within the whole city, there were 129. And so those bar graphs and some of the bar graphs that Chima was looking at have a lot of inherent value attached to them. So I kind of wanted to look at that. One last one, and I don't want to say wasting everyone's time, but there is another paper that we have here, William Satterwhite, because you guys know, anyone know William? He was a criminal justice major. But this is the paper that he did. He was looking at what happened to crime rate between 2019 and 2020. We picked out crime April, May, June of 2019, April, May, June of 2020. We picked out those 3 exact months so we can maintain consistency. But you can see exactly what we did. This table of contents ring a bell? You bet it does. This is taken right from his position paper that he just renamed thesis and we worked on together. We put in something called a table of tables, and I can give you this raw document here so that you can go make your own table of tables here, because I forget how to do it. I'd have to go Google it. It'd probably take me 45 minutes to go through and do something like that. because they have certain headings. Because I'm not going through and typing all those in by hand, you know what I mean? I'm just referencing the little table down there that's got a certain heading that brings it back to here. Okay, and you can see here when converted, it didn't like that one. Usually bookmark not to find. I'm gonna blame William on that one. But you can see the process by which we made the data. We did some geocoding like we talk about in our class there. You know, we have crime rates of 2019, crime rates of 2020. Hey, let's average up all these crime rates versus averaging up all these crime rates. Same thing that V did. You know, instead of suicide rate, so we had to go through and calculate the crime rates. So we counted the number using that spatial join that we talked about in week 1, normalized by population. And so we just looked at this crime rate versus this crime rate. And then while we were there, hey, we've got some general statistics. This is how many of these geocoded correctly. But we can see it went from 41 down to 32. And I wanted to highlight it. I wanted to kind of pass the exam. And so we used the one-tailed t-test because we made a statement that said, we tried to prove or disprove that crime rates went down. Okay. Crime rates went down with that one-tailed t-test. Now, I didn't say crime rates changed. Crime rates went down. Where that Chima said, there's a difference between rural and urban. I don't know what that difference is. It's just different. And so statisticians will kind of get a little emotional about the wording for those. I won't get as emotional about those. But then we also looked at clustering. We have fancy stuff right here that we're going to look at from a reading. But we looked at the cluster of hotspots. The hotspots change. You know, we can see I kind of got a new hotspot here. The cold spots are largely the same, but the tenor of crime between 2019 and 2020, even though it went down, you know, 30, 40% or whatever we were looking at, it largely stayed in the same places. Now, maybe someone in this class might want to go and, hey, I want to get the motor vehicle thefts. I want to get the part 1 crimes. I want to get the violent crimes. Like, I could have took all crimes. It could have been like runaway teen, abandoned cars, you know, something very innocuous versus, you know, hey, I want to look at my violent crimes, because what William did was we started to look at the different crimes. Hey, here's some nice descriptive statistics here. Hey, number of hotspots in 2019 went from 20 to 21, from 5 to 6 for cold spots. Okay. These are something my kids could understand. And then when we look at the actual types of crimes, this is what we talked about in crime class today, where we run something called a summary. Count how many times a zip code appears. Let me look at all the crimes here. Simple assault led the list of all the charges in 2020. It went from 3rd to 1st. Burglary, vandalism, aggravated assault. I don't even see aggravated assault on this list here. What does that tell you? During COVID, since people are around each other, you know, they get really annoyed with each other. We get aggravated assaults going up. So these are real basic, I wouldn't even call these statistics, summary statistics. These aren't even descriptive, summary statistics to say, oh, cool, look at intimidation went up too. Wow. You know? And so the person-on-person crime really started to increase, although crime went down. So this is the position paper. You can tell I get really passionate about the position paper because, you know, I can give you exams and all this other stuff and test you for this, that, and the other thing. But I like giving my ratings because so you can understand what I'm writing and give myself a little pat on the back that people are still reading it. But being able to interpret the results and then you being able to replicate something like that. So you could be putting stuff in one of these papers as well. So that's kind of my long about way of talking about this. But today we're going to talk about point patterns. We'll take a break after this, and then we're going to start working on the exercise, because a good part of the exercise, once again, is data prep, data prep, data prep. You're not going to get these inferential statistics ready to go, because a lot of times when we look at points here, this is a map of supermarkets. Okay, these are just a bunch of points here. And we had a former student who did her PhD over at UNCG who wanted to look at the spatial patterns between supermarkets versus convenience stores versus farmers markets. Now, there's a lot more convenience stores than supermarkets, and there's a lot more supermarkets than farmers markets. And when you put them on a map, they just look like a bunch of points, just a bunch of points. And so obviously we can't do things like density mapping because obviously there's a much higher density of convenience stores than supermarkets. But we can look at the clusters of where they're high and then also look at the point patterns related to these. We've got a couple of, part of the exercise today is going to be really neat where we had a student in field mapping class went and mapped all of the emergency call boxes on campus. And we want to see if they're clustered, random, or dispersed. Now, this is some other data out there. This is food access. I just thought this one was me. I was born down in Rhode Island here. And then what we can look at, this is the percentage of mail-in ballots for the 2020 general election. This is the percentage of people who literally mailed it, never showed up at a polling place whatsoever. And the interesting thing about these is that these are spatially related. Now, who made this map? Who made these colors? Who made these divisions? I did. Me. I did.
Okay.
Yeah, someone did.
Yeah, yeah.
So this thing can lie. This map doesn't lie. Now, when we look at clusters of mail-in ballots, you can start to see where the hot spots and cold spots are. And next week we'll talk, or in a couple of weeks, we'll talk about the hot spots and cold spots. And a hot spot is just a high value surrounded by a high value. What's high? Bigger than average, more than average. We know how to calculate the average. This doesn't lie. My maps lie. So we can make maps like this. Mail-in ballots. Now, if the whole thing were yellow, which it's possible, just means we got largely random distributions. So the more reds and the darker the reds, meaning we've got 95% confidence. That P equals 0.05, which should be like 99% confidence as well. And so we can look at COVID as the election, the general election of 2020. And so you can see where COVID hotspots and cold spots are. Now, the one thing we had, and I kind of go back to this before, is that when we start mapping densities, we have to, especially with that previous example, we have challenges in mapping densities of convenience stores versus supermarkets versus farmers markets because, well, there's not as many there. We know the density of one is going to be higher than the other. When we look at like the average value to average distance to the nearest store, we don't highlight travel methods and measures is not specific, generation of COVID rates. And so we run into all these challenges, just like we have with death rates, because when we map death rates, we're just mapping where the old people live, for lack of a better term here. And so how do we kind of express these inferentially? Because what we want to do is analyze patterns and look at the adherence to Tobler's first law of geography. Tobler's first law, and I talked about this very first week, is that things that are near each other are more related than things further away. So you live in a neighborhood that has a certain income or votes a certain way, guess what? Most people are probably going to vote a certain way. I always like looking up the voting patterns in my registered voters in my neighborhood. And it's 13-9 Republican Democrat versus independent. You kind of move over to across the street, it's probably going to be about the same. You go to another neighborhood, it's not going to be just next door. It's not going to be 20 Democrat, 0 Republican. It's not. So we're going to see these gradations gradually change. So we're going to analyze patterns. So we can do global calculations, kind of like our means, median, modes, range, which express the entire data set. And then later, next week, we're going to get into local calculations where we have a z-score, p-value, or anything like that, where p-values are generally be expressed for the entire data set. But what is this polygon right here? Is it red? Is it yellow? Is it blue? Okay, and those are called local calculations. So we're just extending these to spatial data. Now, what we look at, a lot of times when we look at points, we look at dispersed to clustered. And we talk about this thing on a continuum, meaning all the points close together, they're clustered. If they're far away, they're dispersed. Now, with both clustered and dispersed, there is intentionality with these. Meaning I throw an inferential basically means how does it compare to random? If I were just to magically throw 50 points up there, what's it going to look like? Some will be close together, some will be further away. They're not going to be all equally dispersed. So things like McDonald's, they are by nature going to be dispersed. We're not going to put two McDonald's right next to each other. Where that crime might be clustered. And when we look at our class and we look at the homicide crimes in Durham, you know, they're all in a certain neck of the woods right there up in East Durham there. Okay, most of them. Yeah. And so there's intentionality with these where that randomness doesn't display that intentionality, but how do we express that using a z-score? I've got some formulas written up here. There's something that I love doing called a Poisson distribution. So when we talk about spatial autocorrelation, it's just a big fancy way of mathematically and statistically expressing that things that are near each other are more related than things that are further away from each other. Spatial autocorrelation. So the confirmation of Tobler's first law of geography, we can use similarity, we can use probability, and we can use correlation. Correlation we'll talk about later here, but I like the idea of probability. And this next few weeks are what we call inferential statistics. And in particular, spatial inferential statistics. How do they compare? Now, these days, we got these nice little tools. It flicks it and it just makes stuff and we pop it up and we need to write about it. So Tobler's first law is that everything's related, but near things are more related than distant things, whether it's income, who we vote for, anything that you think, how long it takes you to get to work. I bet you can put those on a map and see spatial relationships attached to those. So when we have positive spatial autocorrelation, we've got high values surrounded by other high values. This is population density over in Puerto Rico. Intermediate values surrounded by other intermediate values, low values surrounded by low values. This is what we call positive spatial autocorrelation. This is how, to me, I think the world works. Highs near highs, low near low. I don't know what we're mapping here. Maybe population density. It could be population density. It could be income. It could be reading levels. It could be education attainment. I don't care what it is. Even things that you think are random, like ADHD or birth defects or ulcerative colitis, they're going to have a spatial pattern attached to those, where that we have negative spatial autocorrelation, where it's got this checkerboard pattern right here. Highs next to lows, next to mediums, next to whatever. And so you can see the highs next to the mediums, next to the lows, next to the middle. Yuck. Okay. I don't like this because this proves that geographers are really people. They need us. Okay, they need us. Where that and a lot of times we'll hear the term stochastic to describe these. So we've got these inferential statistics that assume data comes from a random sample or a randomized experiment. And that's what I was talking about with NCCU versus North Carolina A&T, where we go and measure just 50 random people. And Fred can probably tell you creating a unbiased sample is an impossibility these days. When you create an online sample of things, it's not really unbiased because it's only limited to the people that have access to the internet. Believe it or not, there's lots of people out there that do not have access to the internet and they live perfectly normal lives and they don't, check their, Insta thing and all that other stuff. They're people, they have perfectly good lives doing so.
And the IRB got approved.
And the IRB internal review board that has to approve it. And they meet. So if you do things with taking surveys of people. That's why I avoid it at all costs. It is not,
It's not.
that's not fun. Lady who runs it, real nice lady, but a lot of. So, but we assume data come from a random sample or randomized experiment. And as with the mean, statistics must have a relatively large number of cases. Okay, so like I said, if we were just gonna be me, David versus Goliath, sort of scenario, where just me versus some random person from A and T, I might be taller, I might be shorter, or whatever. Maybe we could stand the center of the basketball team or whatever, but that truly isn't random. The other thing we have are confidence intervals. They're used when the goal is to estimate population. So we are 68% that the confidence. So now when we start converting these z-scores to confidence intervals to p-values. Now we're going to just let the computer do all this stuff for us. So we're not going to mess with all of these. To me, there's no correct method for inference from data haphazardly collection of bias of unknown size. I always like working with certain sample sizes because a lot of times if I have a whole bunch of points there, well, what am I looking at? I got to group these by zip code so I can get an adequate number of zip codes, counties, which Chima did and VU did. And so the other thing is the mean is strongly influenced by a few extreme outliers. Outliers can have a large impact on your confidence interval and enhance your results. And so in some cases, we had to address, and we'll talk about this in chapter 13, small number issues. Meaning, we had a couple of zip codes. Hey, we were looking at breast cancer mortality along the entire, state of North Carolina. And we had a couple of zip codes that had like really high rates. Why? Because they had like one person of the 5 people who lived there died of breast cancer. That's a 20% death rate, from breast cancer. What do you think that did to the rate of everything else? Bopped it up. What do you think that did to the hot spots and cold spots? It manipulated those hot spots and cold spots. So I said, hey, any zip code with a population of less than 500, we didn't use it. Not only because of the zero values, you had 2 people. What are the chances of one of them having cancer? 0, probably. So we had a lot of zeros, a lot of high values. We got rid of those. So we kind of got rid of those. So you see values that look like this, where we have this random generation I don't like. And so when we start looking at this, all we do with the two-tailed t-test, and I know I'm getting ahead of myself because I'm so excited, is that we compare this normal distribution for one set of data versus the normal distribution for another set of data and see how well it lines up. If it lines up nicely and neatly, then guess what? They are statistically the same. If it goes far enough away through these one standard deviations in one direction versus another direction, they're statistically different. Because we're not really comparing means, we're comparing distributions. And so that's why Chima in his calculations put the variance, just in case, like, hey, 2 values had similar differences, but different p-values because their variance was calculated slightly different. And so when we convert these to these confidence level, we can see the approximate z-scores that we have. So a z-score of plus or minus 0.165, and that z-score will be dependent upon a number of things there. But that z-score in science-based research, we're typically looking at 90% or 0.1, 90% confidence, 0.1 p-value or confidence level. Statisticians, as many statisticians as there are out there, they have as many terms to describe this as well. But we're going to see something called a t-value that's derived from the z-score, and then that will be converted to a p-value. And typically when we look at a p-value, this is what ArcGIS Pro generates for us. It generates this nice little curve right here, and it'll tell you, hey, look, if you got a p-value of this versus this versus this is your confidence interval. And so when we run it, when we look at points up there, hey, how does this set of points compare to the observed versus the expected? Expected is going to be the random. And so we can just compare it to there. So we have a number of different methods here to compare these. Me, I'm a big quadrant analysis fan just because it uses GIS. I've created these big tutorials on it. This book here, and I've kind of scanned in this book as part of the chapter, has a really good part. I think it's chapter 3 on point pattern analysis, how to create, identify patterns, all this other good stuff. You know, super. What's that?
Scanned it in the system.
Yeah.
For.
Yeah, I scanned it into the, I scanned in modules, yes,
Okay.
yes. And so one of the things we create something called the quadrant. Now we've got big fancy formulas here. We know what this one is here. Oh, yummy, look at this thing. Now, guess what? Who knows, what's the little exclamation point? Is it yelling at you?
Maybe. Dr. Lord, I was gonna say, you just.
Yeah, this is a factorial notation factor with this little e. Euler's number 2.18. But guess what? This is called, we don't have to worry about this because Excel has
Yeah, everything.
Excel has calculation for this. Now, what we do with quadrant analysis is that we superimpose what we call a grid, a lattice. ArcGIS Pro calls this thing a fishnet. So it superimposes this fishnet on top here, and it counts the frequency of points. Why do we like putting fishnets on things? What's the advantage of putting a fishnet, these grids on top of a set of points and just counting, oh, 2, 1, 2, 3, 1, 1, 2, 3, 2, 2, 2, 1, 3, 2, 3, 2. What's the advantage of that?
That's squares.
It's squares.
Textual.
And textual, it looks prettier, right? The other thing is, do I have to calculate the density?
No.
Why? Because they're all the same size.
Yeah.
So if they're all the same size, I can just count 0, 1, 0, 0. Oh, there's more here. So I can superimpose these. How do you count in GIS? What operation would you use to figure out how many points are in this one versus this one versus this one versus this one? What function is that? This is from week 1.
You could select by location.
Oh, you can. That'd take a long time.
Okay.
What about spatial join?
Oh,
Spatial join.
yeah.
Create the fishnet, create a spatial join that just superimposes everything on top.
Oh,
Yeah.
okay.
And so I'll get a spatial join, I'll get a frequency. Now, instead of cancer death with counties, I've got grids with number of points within it. Because a lot of times we start now, what is the size of the grid you want to create? Okay, we can create lattice sizes here, and it's got a nice little formula here. I'm gonna do that everyone. I'll put it right here for everyone. But the formula, I don't know if I can say it here. We'll put you all out here. How's that? Okay, but the length of each side is equal to the square root of 2 times A, the area of the total set size, divided by N, which is the number of points. So if your area, we're just going to do some math here. If your area happened to be 1 square mile, so the length is equal to the square root of, and you happen to have 50 of these divided by 50. Well, the length is equal to what? The square root of 1 over 25. What's the square root of 1 over 25 equal to? .04. Let's take the square root of that. Oops. .2. What's 0.2 miles equal to?
Couple of blocks.
800.
Yeah, exactly, yeah. And so if we were to make this lattice right here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It would literally be like a 5 by 5 grid here, and we would put these 50 points right there within these.
And you like quadrant analysis better, but.
I like it better, but we're gonna talk about a couple other things. I like quadrant analysis. Because how many things. I like quadrant analysis better because when you make quadrants and count them, I don't have to worry about densities. I don't have to worry about other things. Now, we do need densities when we're looking at like population. I don't know how many people live in these squares here. So there's certain phenomena that we have, like earthquakes, which aren't going to be deer vehicle collisions, which aren't going to be constrained by boundaries, or we're not going to calculate using deer vehicle collisions per person or whatever. So when we make these quadrants, in some cases we might have too many. So we have too many 0 points. So we use that little formula right there. Now, when we create the size right here, we get like an average number of sightings per cell. Now, my math right here is really pretty here because we have 25 cells. We've got 50 points. 50 divided by 25 equals what? 2. So an average of 2. Here in the real world contextualization, it's going to be a little bit different. But the average number should be 2. If I've got 25 grids, because they're each spread at 0.2 miles, 50 divided by 25 equals 2. Now, the other thing we have is a Poisson distribution. It's a frequency, it's a random distribution of points. It's a random distribution of points that is it's not gonna be even, it's not gonna be symmetrical. Because you can't have, because this is gonna be your number of observations. You can't have like -1 observation, -3. And so it's gonna kind of tail on this end. A lot of times we look at like Poisson distributions for like soccer scores or football scores or whatever. What are the total number of points that are going to be scored here? There's going to be some soccer games that have 4, 5, 6, 7 goals, but most of them are situated about that 0, 1, 2. So, but the good thing about it now, I can make pretty little maps like this. Now, of this sample size here of this study area down in southeastern North Carolina. Now, I would like it here, but why don't I include this area or this? Why aren't, what's going on here? What's
Other than outside the quadrant, that was.
yeah, exactly. It's outside the study area. I don't know. If I were to extend it here, I'm going in the ocean here. It's not really fair, right? Because, all right, you're not going to have any farmers markets in the ocean here. And so you really don't have a full quadrant here. You have part of a quadrant. And here, I don't have the farmers markets data for, say, South Carolina or whatever. And it's outside of my study here. But the big thing that we do is that we compare this observed distribution with an expected distribution. Okay. Now there we can't have 6.3. 6.3, we would just round these. So we have 6, 10, 8, 5, 2, 1, 0. But this is what we have here. And so when we look at our farmers markets right here, the distribution of these farmers markets based on the frequency that we have here looks like this. This in blue is what we see. In red is what we would expect from the Poisson distribution. These are kind of the same, aren't they? Yeah. We run something called a Kolmogorov-Smirnov test to do that with statistical significance. But I like these little charts here. I like the little thing here that says, look at it, they're about the same. And basically, that Kolmogorov-Smirnov test measures the area in between. There. Here's convenience stores. Now, this is the distribution of convenience stores in my study area here. Let's look at what we see versus Poisson distribution, what we'd expect. A lot different, huh?
Yeah.
A lot different. It just tells us that it doesn't exhibit a Poisson distribution, like a random distribution. I love doing this because I love the data prep part of it. Hey, you got to create a fishnet. It really elicits all of your GIS skills that we've been kind of puts them all together. And then we put this into Excel, and then we've got the formula for Excel as well. The other type of point pattern analysis we can do is something called nearest neighbor index. All it is, and it's really simple, is identify groups that are spatially close to each other and uses the test. But all it does is it has a point, it finds its nearest neighbor, goes to another point, finds its nearest neighbor, and all it does is average up all those values and compare it to a random distribution. Just compares it to a random distribution using a variation of this formula that we looked at before. So all it does for every point, it calculates the shortest distance to the next closest point, which is minimized. So it's not going to say the distance from this one to this one. It's going to say this one to this one, this one to this one, this one to this one, this one to this one. So these guys work with each other. This one to this one, this one to this one, this one to this. For all of them. Now it does it in milliseconds.
Okay, got it.
Okay, pretty simple. And so all it does, it compares the observed distance, what it calculated, versus an expected distance. So as you can imagine, if they're all clustered, this distance is going to be relatively small compared to your entire study area, or a random set of points where some are short, some are medium, some are far. And so all it does is we create this ratio. All right, what's the ratio of the observed to the expected? Might be 1. Well, if it's 1, that means the observed is equal to the expected, which means it's random. And then if it's further, if it's dispersed, then the observed is going to be a lot more than the expected. If it's clustered, it's going to be a lot less than the expected. And so we'll assign p-values with those because that average nearest neighbor is going to be a little bit different than this. So you can say, well, I got this point, I got this point. And so our average nearest neighbor is going to be put on a continuum from dispersed to clustered. Now this stuff, don't care about. And we're going to run these later. We're going to run these after the break where we look at uniform patterns, dispersed. If it's less than 1, it's clustered, because clustered and dispersed are statistically significant, random are not. Okay, so that gets a little bit more tricky there. So you can see the formula up there for the average nearest neighbor that I talked about here. It's the observed over the expected. Okay, now what's the expected? 0.5 divided by the square root of n over n. Forget about all this stuff. Okay, they'll just go and calculate this stuff for us. They'll calculate things about your standard error and everything else. So now let's do this again. This is from our student thesis that she did. This is probably like 2017, 2018. Where now I've got convenience stores. Let's look at the convenience stores, because now I can compare the convenience stores, farmers markets, to the grocery stores. And look at those, because you can see with the farmers market, it displayed a Poisson distribution where that convenience stores didn't. So now when I run it, let's see what I get here. All right, I got z-score negative 24.1677. And you can see that nearest neighbor ratio up there is 0.54, meaning the expected distance is almost twice as much as the observed distance. So if you get a z-score of -24, that's way on these extremes. And it tells you here there's less than a 1% likelihood that this cluster pattern could be a result of random chance. This is how they use it. Could be a result of random chance. There is a 5%, there's less than 5% likelihood that everyone, the NCCU students are taller than the NCA&T students. And so when we get another one like this here, here's another one that I ran. The observed distance is 4642 versus 4022. It might need to reproject it if we're displaying these in geographic coordinates, a distance measured in meters here. Our nearest neighbor ratio is 1.15. I get a z-score of 1.67 and a p-value just not quite statistically significant. Just not quite. That's okay. But when we run it, it just tells you, given the z-score, the pattern does not appear to be significantly different than random. So it's just random here for another. But at night, it gives us this nice, pretty output there. So what do we care about? I got z-score, I got p-value. That's what I care about. Okay? All the other things we have are useless. The other thing it does have is something called Ripley's K. I'm not really good at explaining Ripley's K, but it does the same thing over and over again, but for increasing bandwidths or band sizes. And so I'm not going to give any questions on Ripley's K because I'm not very good at it. And so I'm not going to pretend to be very good at it as well. But this is Ripley's K. You can see, and it basically looks at different bands. Hey, as you go further out, we have more clustering from the point versus closer to these particular points here. But what we're going to do after the break here, let's come back at about 6:22 or so. We're going to open up exercise 5 because there's a lot of data preparation that goes into this. And I want to make sure, it's been a few weeks since we've had class, I want to make sure we shore up the data preparation portion of it because we're going to be working with data that you'd like to see that someone like, oh, here's the data, have fun with it, instead of Mulrooney giving you stuff and saying it's all cultivated and curated and ready to go. All right, so we'll take about 10 minutes and we'll be set here.
So yeah, yes, I've got many formulas, but I've never done it in practice. So that's the part that's new. The program that we use when we run system values or we use
It's so much easier to do it.
I see that.
Our studio instead of like. Do you have to take atmospheric dynamics too?
I'm gonna say theory and remote sensing.
Not theory, it's that.
Is that in the spring?
Yep.
I'll be in that class with you.
Okay.
We're going.
Of the remote sensing with Dr. Malhotra.
Oh, y'all have fun with that.
Yeah, I hope so. I just registered on Friday. Got on my spring classes.
Wait a minute, are you doing ABM?
I am, yeah. So my spring semester should be pretty nice because I'm gonna take, I did applied data science in the spring as an undergrad. So I'm gonna be applied data science with Mulrooney last spring. I was talking again this spring as a grad
So the
student.
only thing you gotta do is do the project.
Exactly. So I was turning the project, so that's, yeah. Now I'm doing some social geography class, documenting, and it's going to be a mini master, so it ends in March.
So, is it online?
I think so.
Document this class. Just do your assignment and just click that you submit. Just submit. Don't even put nothing on it. I did an assignment on. Remember I told you about the purple monkeys and the dinosaurs climbing trees, chasing monkeys? What? And I got under it. I was just trying to prove somebody wrong. Doctor, at the time, Dr. Sargent. I said, Dr. Sargent, you can turn in anything you want in this class if he ain't even read. He's like, nah, I was like, watch. So I turned it in, got 100. I was like, see, he didn't even read that.
right. I've met Dr.
Don't
Zardo.
remember that, don't try that, but.
Yeah, I'm not gonna put it to the test, but I'm,
Yes, cause let me tell you, he's got his stuff set. Quick grade,
okay.
so as long as it's submitted,
Yeah,
it graded in every month.
I'll take it. I'll take it. I'm looking for my last spring was rough and this
I'm just
semester's been-
looking forward to this semester, cause the only place I'm even worried about is this atmospheric dynamic with Dr. Bay.
Yeah, what is that one?
I'm not worried about Dr. Bay, I took his air quality class,
I took that one too. That was good.
I love Dr. Bay,
Yeah.
and so, as long as you sit there and pay attention, the Bay is no problem.
Right.
But as soon as you get on his bad side, he don't have nothing for you. Don't cheat. Don't
Right.
ever cheat, because he gonna look at you like, ooh, he's not spraying on me.
Yeah.
But I don't cheat.
But you're working on your second master.
I'll be done next semester.
Oh, that's great. That's great. I'll be done with my bachelor's next semester and then I'll already have a few, grad credits under my belt, so.
You have 9 or 12 under, and just roll right on over.
Yeah.
Nine.
That's
Yeah.
perfect, that's what I did when I got out of the military.
Yeah.
I came in, finished my, had already had associates, came in, finished my last 2 years and right then rolled right into the graduate program. But they didn't have
APM.
over there, like.
Oh, gotcha.
Yeah, they didn't. So.
I gotta figure out what I'm gonna do for this project.
So
Me too. I know, I got this one, I got a crime mapping class on it, or even in that one.
No, I'm just,
I got you.
so I ain't got,
Yeah, that's my thing, that I'm like week to week coursework, I'm doing good with all that, but now all the projects, I'm like,
You know what,
I gotta start
You know what
thinking.
you do?
Gotta start
whatever
thinking.
you do the exact same project for both classes. It would make sense.
Yeah,
just say,
yeah, that is,
Ask him when he comes back, so can I do one project for both classes?
right,
Let's make sure that this one has.
and he's over prime man.
yeah. Even
Yeah, so make sure that it coincides with both
Right,
and add just a little extra for this class.
yeah.
You should be good. I don't think he has a problem.
For, I don't know, do you have to do a paper for undergrad?
No, but I'm gonna do it because
What
next
they
fall.
asked would be this for this.
Yeah,
So
yeah,
just-
cause next fall I'll take this as a grad.
Well, don't even worry about this one. You don't have to do it.
That's true, I can do it next, I can do it.
No,
You
next-
really have to.
Just use the one that you use for project mapping and add just a little bit to it and it's done.
Oh, I got you, alright, thank you, I like the way.
Yeah,
Hey,
I like
let me
it.
tell you another thing too. Because you're taking, you're gonna take this class again, you know all the readings that we're doing already? Go ahead and do them.
Oh, I'm doing them, yeah, I've already done 2, and I look, the third one's due next week, I'm gonna do that third one, yeah, I'm gonna do all the readings,
So
yeah,
you've got what we got, right? Did all the readings,
yeah, so I'm gonna do them.
but they're so easy.
They're easy, yeah, those readings are good.
Yeah, this one, he had a nice one on, I read, with the security fish and wildlife, that one would say. And so I'm from the Northeast and I hunt black bear
Okay.
and did not know that there was a black bear in New Jersey.
Wow.
So I'm like, wow. And so the area where he was talking about, I actually joined the military right there in that area. Did not know there's bears, but they're like that.
Yeah.
You know what I mean? So, but it was, for me, it was a nice read and, and I did go for the weekend. Got it up for it.
I
Oh,
did
that's
mine.
nice, okay, I'm gonna do that reading.
Look, I've already started doing, so what I did was go look at his grades and see what we had left.
Yeah.
So let me go ahead and get done whatever I can. How'd you do on that test? For that midterm?
Oh, 98.
Right. Bitch.
Did good.
Look,
Dang.
it's actual.
I did good. Well,
Look, now I could have done better.
Yeah.
I looked and I put my decimals in the wrong spot. He said, I know you do it.
Oh,
And I seen it
yeah.
and I put it in the wrong spot. And then he changed the grade this morning and made it a 98. I mean, 88.5 instead of 92. I'm like, I don't like B,
Oh, no.
but it's okay. I still got a high A in this class.
Okay, that's good. Yeah, when I did that, I spent I was gonna take the test that, whatever night it was, like on Monday, the night we had class. But I spent 2 hours prepping for it, watching the recording and pre-class, and by the end of it, my brain was fried. So I was like, all right, rather than push through, I'm gonna wait and take it with a fresh mind.
Yeah, I tried to do that, but I got sucked in going to a field trip the day prior.
Oh, that's right, y'all both did that music, so, that's.
I was exhausted, so by the time I tried to crack it open, I had a doctor appointment the same day.
Yeah.
I'm trying to study and.
I couldn't, and then I spent the next whole day, so I was there at field trip, and then I spent the whole next day. We went out there and I shucked oysters all day
Oh, my God.
for my stuff, and then so I didn't take until the following day, the
Yeah,
day after it.
oh,
And I was like, you know what? So I had already filled out that chart. So I knew, and I was like this, and I'm like, okay, and then I could not get one of those questions with the swap lagoon. I was like, you know what? I don't even care.
right,
You can
right,
add it.
yeah. Yeah. That's tough, but yeah, y'all had that field trip right at the same time, that was tough.
Ain't no same time, yeah, you had me locked in.
Shut up.
I ain't have to do it, I was volunteered, you know?
What? Wait, if you ask me to go out, I'd be like, oh no, I'd be mad, but I went. The position paper is usually said second,
I saw that. Yeah, okay.
and number 4, I'll do that later. I'm going to do Ezra number 3 and Ezra.
I already did question number 3.
I'm going to do 3 and 4 and 5. Okay, and 2, 4, and 5. Yeah, I'm going to do all those Ezra, so I'll have that in already.
I get that.
And get this position paper done.
Yeah, but you volunteering, look, I was running away from her.
Who?
Whatever her name was, the social worker.
See.
Yeah. I volunteered, shit.
Come in here Friday, but. Don't call me. I don't know y'all. Oh.
Don't, don't email me, shit.
Email me all you want, do I?
Don't email me, shit.
No. Find it.
Like, you don't,
There it is.
but they were right there, but then now I gotta find the other one,
And add the flag.
what they be on.
It's online. Yeah. I ain't worried about it. That's gonna be the easiest fucking class. Try to.
Okay, no, I got it. But
I don't, not with him. Not with him. Not with that one, really. But no. Got him hard. Oh yeah, sure. Baby ain't, nope. What is that? All right, so we got exercise 5 open, right? All right, good. I see David already has it open. Great. Yeah, we were just looking for, go ahead and registering. All right. All right, we wait. Here. What else?
I do it, I'm trying to remember the
What is it?
number of books.
That'll be it, yeah. Steve Brown. Is remote sensing in an earth science class? Or is it geo? No more geo class. Which one? Yeah, I don't have much of a choice. Wait, you did that online? I mean, not online, the Thursday class here. Yeah, Joe, maybe she got, got 2 classes that are mini. Yeah, online.
But you don't have to take it.
I don't know what,
You don't have to take it. Do you?
I have to TA it.
Oh,
It's just pretty much letting them turn in their homework and I go back and check it. People waiting on you, stuff up, Dave. So, yeah, Until after done. I'm not just secretary. I'm not just secretary.
I moved one, I wrote it down, but
Okay. Here we go. Okay. So just make sure everyone's following along here. We're gonna click on modules. Couple things that I have. Under week number 7, I've got, first thing we have is reading number 3. So that's gonna be due next week. This is a reading that I did about the about bear sightings in northwestern New Jersey. I've probably said this story before, but my brother was working on, he was always interested in that stuff, and he was working on this as part of his master's at UNCG. He passed away, and his wife gave me like all of his stuff, like all the data he had. So I was like, all right, let me go complete it. And so it was pretty neat project, but it talked about, where I got the data from. It was AdXY data. They had the GIS data there, because most of the maps made by the Department of Fish and Wildlife were largely at the county, not county, township level, because counties are subdivided in township, boroughs, and cities. So you live in a certain township, and that's where police officers and schools and all that other stuff, not based on your actual town, your mailing address. And so I created this, it was pretty neat, but you notice here, these formulas, I created a quadrant map right there. That's all I did. So this is actually up in Passaic County there. You can see the cluster analysis. What I do, I did a little Poisson distribution, and then I did some cluster maps here. Real nice cluster maps with hot spots and cold spots and all that other good stuff. So what I'm going to ask you to do is you're going to read the paper, answer the questions about it, just interpret what we do. That'll be due next week, this week, and then for exercise number 3 or exercise number 5, I've posted the presentation, I've posted the video. So what we're going to do is we're going to download the exercise. I've already got it here, but in full disclosure, I'm just going to show everyone how we do it in case we forgot all that unzipping stuff here. But I'm opening up in Chrome, open up in my folder here. You can see this is a zip file. You can see it says over here, type compressed. I click on it here. You notice when I click on this file here, it doesn't say unzip. Click on this file here, it says extract all. Okay, so we click on extract all. Where do I extract it to? I'm just going to extract it to my downloads, but you would extract it to your flash drive or the folder or wherever you're saving it at. I can't stress the importance of data management. These days with stuff in the cloud, I think students have gotten a lot better, but I used to have someone like walk in with their computer. I can't find stuff, and
I know.
but I can't find it either. I don't know where you saved it, Let's start the downloads and go from there. But you can now see I got an exercise 5 here. And then if I were to double click on this, you would see the APRX. And when I double click, I can open up the APRX file. And you can see I got a lot of things going on here.
Yes.
I've got table of contents. I got NCCU call boxes. We're going to do a little, we're going to do a little exercise at that at the end. But I've got multiple data. I probably could have put these into multiple maps, but I just put them all into one map. So you could you figure it out sort of thing, because this is what kind of raw data looks like here. You can see I've got an outline of the counties here in our study area, which go from Durham over to Forsyth County. And then I have a map here, a layer here of all of the deer vehicle collisions within the study area. I had a student, he did his degree in ecology over at NC State, and then he came here for his master's, and he was always interested in like deer vehicle collisions. So we found a data set here, and now he's an estimator over for a real estate company, if I remember right here. Let me see, I think I'm connected to him. Okay. Yep. Heavy civil estimator. This is him. Yep. So Eric, he's been a while since he's been here. But-
Seniors.
Yeah. And I'm just about positive what he does is that, he did his conservation biology and he came to us here. He did stuff with hiking trails, change detection analysis, impervious surfaces. But what, and he also did with, real estate, market velocity, price points. But he does, I think, like large scale photogrammetry, using GIS, using data, using mapping to figure out how much it's going to cost to move land, all that other
Yeah.
good stuff. So, but you can see the word senior in front of his name. That's pretty good, really
Damn
good.
good.
Really good, but good rep from our department here. But he was interested in deer vehicle collisions. So you can see, we got a map. I got all the data of deer vehicle collisions here throughout this particular study area here. Are they random? Are they dispersed? And these are going to be the bigger questions that we ask. First thing we're going to do here when I look at exercise 5. What's the significance of the Poisson distribution? I've got a couple of videos up here. Go to them. So I got a video here on nearest neighbor analysis, and then I got one here on Poisson distribution. It has gotten 2,900 views over the last 4 years. So 2,900, almost 3,000 people have found the interest of, found the interest of it. So we've got that, but we're here. I think we're doing Poisson distributions for one of these counties, and I go through the trouble of extracting out the data, some of the nuances of kind of, all right, how big are our quadrant sizes? What do these quadrants include? And hopefully today we'll be doing the same thing. So those of you kind of follow along here, hit the pause button. So when I post this tomorrow morning, we can go back, go forward, and all that other good stuff. Because it gets a little convoluted like we did first week where we did that spatial join. How do we do the spatial joins? We're going to do spatial joins. We're going to do summarizes here as well, in addition to creating some fishnets. So when I look back at this question, what's a Poisson distribution? Okay, cool. Okay. For a given study area, if the number of points were to increase, what would happen to the quadrant size? Let's go to this formula right here. Length equals the square root of 2 times A over N. N is the number of points here. This is kind of applied stuff right here. We're looking right here. The length of the side equals 2 times the square root of A over N. If your number of points were to increase from 50 to 100, what would happen to this length? What happens to it? If the denominator goes up, what happens to the number?
Get bigger.
If we go from 1/2 to 1/3 to 1/10 to 100, it's smaller. So the length of this, so basically you're gonna get more and more what? Quadrants.
Okay.
L is equal to that length of the quadrant, because I have these nice pretty numbers here with like 0.2 and all that other good stuff, but we're not really working with 0.2s. Okay, so the first thing we've got here. Okay, we're going to look at the distribution of deer vehicle collisions in Caswell County versus Rockingham County. You will need to extract out the points first, because what we're going to do is we're going to do some quadrant analysis for Caswell County down here. We're going to do some quadrant analysis for Caswell County. Okay. So most of you maybe noticed here in the table of contents, what do you see? Well, we're already exported out the counties, and he didn't already do it on purpose. He did it by accident, but he's already got all the deer vehicle collisions for Caswell County exported out. Well, what did he do? I'll show you exactly what he did. He went and selected Caswell County. So he selected Caswell County. He went to all the deer vehicle collisions, and then he did what? Select by location. And I want to select what? All of the deer vehicle collisions that intersect with.
Dr. Martin, can you back up a little bit, because I wanna select my location,
Yep.
and so when you select, you just polygon, just select.
Yep, select by location. Now, what I did first, and Fred's got a good question, was that, well, I had to go pick out Caswell County, because if I just selected every deer vehicle collision that intersected with every county, what are you gonna get? All the deer vehicle collisions, so I used this little select button. And I just put a little rectangle here in Caswell County so that it's highlighted in blue.
Okay.
It's highlighted in blue. So-
When I select.
Click on rectangle, and then click on rectangle, now, right there. There it is.
Okay,
Okay. And then. Now select by, now I could have gone into the attribute table, I could have got a query, county name equals whatever, but. I went through the trouble putting the labels here so we could pick those
Okay.
out. And I'm just showing what you did because I already did this thing here. So I'm gonna do select by location. I'm going to pick out all of the deer collisions that intersect with what? The counties. And I'm gonna click the little button that says use selected features. Why? Because we went through the trouble of picking out using the selected features. Now I'm gonna click apply. And there it is. So now when I look at these exercise 5 deer vehicle collisions, you can see there's 115 out of 3,930, 3,393.
right.
Okay. Now, if I wanted to export these out, I would go right mouse click, data, export features, and I would call it, Caswell County, Caswell deer vehicle collision. But guess what? Well, I've already done that. So now I've got Caswell deer vehicle collisions. Now, I've got 115 or something like that. Is that what it was? 115. So for one of the answers, you could put 115. For the other one, for Rockingham County, guess what? You can go and do that later. Okay, but you would do the same exact thing, but instead of selecting Caswell County, what will you pick? Rockingham County. Okay. Because for 1 and 2, you're going to be doing the same thing. And I'm asking you which data set's more clustered, but you can go through the trouble of doing Rockingham County later and kind of recording this as well. Because I went through and picked out Caswell. So the number of deer vehicle collisions per 100 square miles. What's the formula for that? Number of deer vehicle collisions per, because what did I have? I had what? 115 here, right? Oops, I gotta enable editing. So I really had what? I had 115 total collisions, but is that county big? Is that county small? What's the deal with that county? What's the formula? What's the formula? And this kind of goes back to the exam. Do I want to find out the number of, how can I calculate the number of deer vehicle collisions per mile, per square mile? How many square miles are in Caswell County? Can I figure that out?
Yeah.
Of course I can. Let me go over to the counties. I bet you there's somewhere over here that has the word area. Do you see anything here that says area?
Square mile.
Square miles, 428. So when I go to this, what is it? 115 divided by 428. That's a really, really small number. 0.268. So what is, when I calculate per 100, what do I really do when I multiply? So this number,
Oh, you just want to get rid of those decimal spaces.
yeah, divided by 428 square miles equals what? 0.2682628. I'm having a rough day. 2689 per square mile. But I didn't ask for per square mile. What did I really ask for? Per 100 square miles. When I multiply it by 100, what am I doing? Moving the decimal point over how many?
Two.
Two. So 26.89 DVs per 100 square mile.
So that's what you.
That's what I want. Exactly. That's
Do you want
what.
us to put all that in there though?
No, I just want the answer. That's all I care about. Now, you're gonna go back later and do this for Rockingham County. Okay?
Yep.
Mhm. So this is my answer right here. Ding, 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 right here. This number here. Because a lot of times, well, the 0.26, what does 0.268 deer vehicle collisions really look like to you? Is it like a quarter of a car that's injured? or- Exactly. Kind of like homicides. What does 0.003 homicides look like? I know what 3 homicides for every 10,000 people looks like.
Yeah.
I know what 10,000 people looks like. Even though 0.0003 per person is the same thing as 3 per 10,000, it's just, I can wrap my brain around it a little better than these per capita numbers. Okay, so next thing we've got. You'll do the same thing for Rockingham County. You'll extract out the data, do the same thing for Rockingham County. You're gonna do the same thing for Rockingham County here. Now, what we're gonna do here is we're gonna run nearest neighbor analysis for Caswell County. You can go back later, click the save button, do the same thing for Rockingham County. Yes,
I have a quick question.
yep,
Okay, so up in Rockingham County where you got those deer, the
EV collisions, yeah,
Okay, so right here online, I'm looking online, and I
yeah.
have the exact same thing you have up there. How do you get it where you're showing that you see this 115? Where do you see
Okay.
this 115?
I do right mouse click on,
On which
Oh,
one?
oh, the 115 is for Caswell.
It's that, well, okay, I know that,
And it,
yeah,
but,
with the
but-
number.
right mouse
Okay.
click, open attribute table,
Exercise 5.
down here. 115.
okay, and that was on the exercise vehicle.
Yep, and then also deer vehicle collision, since I exported it out.
Got it,
115. right
okay, I just wanted to make
there.
sure.
Yep, 115 right there. Alright,
Thank you.
so I exported those out.
I didn't get them. I
There
was
we go.
making sure, wait a minute, I don't see 115 anywhere, but they said.
So now we're gonna run nearest neighbor analysis. So we're gonna click on analysis and tools, tools. And I'm gonna go over to toolboxes. And I'm gonna click on spatial statistics. So toolboxes. These are all the different tools. And then we're gonna click on analyzing patterns. And then average nearest neighbor.
So did you put spatial statistics?
Yep. And now the other thing I can do is what? I can go into find tools, average. Nearest neighbor, if I know what I'm looking for. So up in the top, I can just type in the words average nearest neighbor. Do the same exact thing here. I can click on toolboxes, spatial statistics, analyzing patterns, average nearest neighbor. Same thing here. All right. What I like to do, or I don't like to do it, but show everyone is look at the help. What does it expect? Input parameters, all that other good stuff. So what we're going to do is we're just going to see of Caswell and Rockingham County, what you're going to do later for homework, which one's more clustered or less clustered. And I can click the little button right here that gives me, all the information about the tool. Do these things recognize, we recognize all these. We can publish reports, publish reports and all this other good stuff here. And actually, how does it actually work? So you should see some of these formulas right here that we've had. So the input feature class is going to be what? Caswell. So I see the word Caswell deer vehicle collisions. My method is going to be Euclidean. Just for the heck of it, I'm going to click generate report. All right. Drum roll, please. Here we go. Let's see what we got here. I'm going to click view details. All right, what do these details give me? The observed is 4118. The mean distance, because to me, looking at it through my eye, I wouldn't know they're clustered.
P value, got it.
So, what do you think 4,118 divided by 5,014 is? 0.8212, yeah. So that means that the observed distance is less than the expected distance. If we were just to throw 115 points up there. And now the z-score tells me it's negative 3.66, a little on the far end. And that tells me that there is a very little chance that this is a result of random. Now, just for the heck of it, I stored it here under my class homework stuff here. Now watch, I can click on this. Now I got a nice little graph here that it made up that says, got a little graph. It tells me right where it is. Look, it's got a little dot right there.
Okay,
Thank you very much. There it is, got a little dot. It says, look, it's got this, got the piece for it. You can screenshot this thing, stick it into your PowerPoint presentation, and you're good to go.
And that will generate for us when we do it every.
Yes, if you click generate report. Now you're writing a paper like, hey, I'm going to do a paper on the clustering of motor vehicle thefts in Durham. This is it right here. You already got a p-value right there. Motor vehicle thefts are clustered in Durham.
If we hit to highlight the link, it's
Yep.
going to give.
That'll pop up.
Yeah, I just did it. It won't work.
Yep. Or, hey, I would go through a find a crime in 2024 that wasn't clustered, because you would imagine there's most of the crimes are going to be clustered. Hey, let me go through and pick out 6 or 8 different crimes and let me find what that isn't clustered. Now, what would that mean? What would the p-value of something that isn't clustered be? 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, where these observed and these expected are close to each other. Yep. So those of you thinking here, I need a, I need a topic. You got one. Okay.
Yeah.
I was sitting here thinking too.
Yeah, talk to Chima about getting the crime data. Because we got the crime data all, you got the crime data. Talk to David. This is David here. He's got all the crime data from our crime analysis class. And he knows how to make it all because he learned a geocode last year. So yeah, that was hard. Or add XY data. All right, but we already got this thing. Once we start getting p-values, statistical significance.
Yeah.
Okay, you got a paper, right? You got a position paper right here. And to me, with the position papers, don't make it more difficult than what it is. You know, you got 5 pages, explain, do a little background information. What about crime? Is crime clustered? I don't know. And so, where does crime data, what are previous studies on crime data? Just a little practice. Yeah. Okay. Now, what you're gonna do, okay. I didn't mean to say. But what you're gonna do here for exercise 5 is, what do we got? We got an observed distance, expected, nearest neighbor, z-score, p-value. Cut and paste all those in.
Yep.
Do the same thing for Rockingham County when you export the data out, and then you're gonna tell me which county is more clustered. Which county would be more clustered with the higher z-score, lower z-score? It's kind of a trick question, I bet. What about the p-value? Which one of these numbers here of observed, expected, nearest neighbor ratio, z-score, p-value would tell you which one's more clustered or less clustered?
I'm gonna say the observed to expected because it's
Exactly. Yeah. Probably this ratio right here, whichever one has the higher ratio, the one ratio closer to 1 or even above 1 is going to be more random than this one. Because the observed is only about 82% of the expected. The expected is, I have 115 points. I throw those 115 points randomly over my shoulder, and my observed is only 82% of that. Now, if it were 100% of that, i.e. 1.00, then the observed and the random, there's no difference between them. And so that'll make that p-value go up, that z-score go closer to 0, because that z-score in the other direction positive articulates dispersion, which is a totally different can of worms. It's hard making dispersed data sets, like lattice, lattices or things that are equally far apart. Okay. So we've got that one there. Next one, we got number 3. You're going to be working with both data sets. Just run the Ripley's K. You tell me what it gives you. Go through the help real quick. I'm not a good Ripley's K person, so just run the tool. What does it tell you? Because my student who did this would really love Ripley's K, and I did not see. So
there's a tool in there?
Yeah, you just type in the word Ripley, and then you can see multi-distance. All it does is it creates this clustering at different bands, 1 mile, 2 mile, 3 mile, and the computer picks it.
Okay.
Yeah.
Got it. Okay.
So statistically significant, I just never really saw the value in utilizing Ripley's K, but I just want to, make sure you're able to interpret and understand the results of it.
Got it. Okay.
Yeah. And that's the big thing. These computers are powerful.
So on the Ripley's K, just which distance and spatial cluster with Ripley's K.
Yeah. So does your conclusion from number 2 match up the conclusion from number 3? This answer should say 2. Yep.
Okay.
Those of you watching this, the answer should say number 2.
Oh,
Yeah.
mine.
Should say number 2. And if I think of it, I'll put a correction in there because I don't want to give everyone, I don't want to post a new Word document because some of you have already downloaded and are working on it. All right, now this is where this is what I like doing with the data prep, now we're going to go and run quadrant analysis for Caswell County. All right, now we're going to apply this formula here. We're going to create a fishnet. We're going to overlap it. We'll stop in about 15 minutes here and let you all kind of take off the rest of them here, but we're going to do some math. Okay, so those of you looking right here, we're going to do some math right here. Let me pull this out for a second here. So our length equals the square root. We would want to create a fishnet. We want to create that nice little lattice, Lattice, L-A-T-T-I-C-E. ArcGIS has used the term fishnet. I've just disconnected everyone, but I think you can all see me, right? I hope. All right, we'll be back in a second.
I'm not
Oh,
gonna turn that back
you can-
right off, because you can't, when we looking back on the video, that glare makes it where you can't see that more.
Okay, well,
Okay.
we got this one here. We'll see how it goes for the rest
It's
here.
free to fish tank.
Okay, so we're gonna create a fishnet right here. Now. You see the questions here, L equals the square root of 2 times A. So our length is gonna be equal to the square root of what? 2 times, what's the area that we had before from that previous answer? 428? 428 square miles?
Yes,
428 square miles. What is your N in
Well, the 115 days.
115? So when we calculate this, let's do some math here. 2 times 428 equals that divided by 115 equals that. I'm going to take the square root of that and 2.72. 2.72. Just for the heck of it, how many feet is that? And I'm asking this for a reason.
How many feet is that?
Yeah, feet. How many feet are in a mile?
1816?
what?
5,280.
Wait a minute.
5,280.
Yeah,
Yep.
okay.
So approximately 14,405 feet. Now,
Ah,
I just want to keep that there because the projections we're working in are in state plane feet. So when it asks for the size of the fishnet, it's based on the projection, which is in state plane feet. So if I put 2.72, it's going to make a grid 2.72 feet in
Okay.
size
yeah,
versus 14,000 square feet in size.
Okay, so which one do you want to answer?
I don't know. I gotta plug stuff back.
Okay.
Put this out of everyone's. All right, I'm plugging it back in here. We're back.
Hey, y'all. Miss y'all.
All right. We're back. Okay. And so for these answers here, what are the number of points in the county? 115. What's the size of the county? I believe it was 428 square feet. What's the quadrant size? 2.72 square miles. What is the quadrant size in feet? 14,405 square feet. No, 14,405 feet, not square feet here. Okay. Let's skip number 5 because we're going to go right to our quadrant analysis. This is a sample quadrant analysis here that I've run and that you'd be running for. This is, and all we did, basically I'm going to show you here. I already have this answer here in exercise number 5. So if we click close, go back to our modules, I have a sample under week number 7 of my quadrant analysis example that has the formula.
oh,
Has the formula sitting right here. So all this nasty formula stuff here, it's already there.
nice.
Already there. Now, this thing, we're gonna have to worry about this thing that up there in a second. But our count, observed, Poisson distribution, expected. And now we can go make some nice pretty little graphs right here doing insert. Oh, look at that thing.
Oh,
Look at that.
Wow.
Boom. That just happened. Well, we're jumping ahead of things real quick. So, but I've got this Excel, I've got these things here with the Poisson distribution, where these numbers come from. And so we're gonna have to use our GIS skills to create these. Okay, I love this Poisson distribution. So we're gonna create this Poisson distribution here. Now, what I have here also, just for the heck of it, I also went and created what? Fishnet of Caswell County. It was not an accident. It was an accident because I wanted you all to create it. But I can go to geoprocessing and type in the word fishnet
For that,
and create fishnet right here, and then I can create an output feature class. I can create the cell size width in feet, 14,405 square feet. And then I can specify the number of rows, and then I can also create label points when I don't like to do. And then under geometry type, we definitely want to put polygon because we're going to do what? We're going to count the number of times each of these points occurs within each of these.
yeah. Got it.
Yep. And so we're just going to run a nice spatial join with these. Okay. But this is how we create the fishnet. Now, some people from time to time, they grow brains. Watch this. We do test here and we do like 2.72. Because remember, computers are stupid. 2.72. And then I run this thing. Uh-oh, what am I missing?
I think you need a number of rows, a number of columns.
No.
Why,
Number of rows. Cell size X. Well, I've got the right one here, so.
Okay.
I have to go play with this a little bit more. Environments, output coordinate system. Right. There we go. Okay. There we go. All right. I just clicked on the little map to specify the extent of it. So all those big nasty numbers that came in are the coordinates in feet. Now I run it. What happens? Oh, look at that. What happened? What happened? I went and created it at 2.72 feet and it says, hey, I got a couple billion.
Oh,
I-
yeah.
Yeah, and it's already, so you don't have to do it.
Can't do that. Cannot do that. And then I can click X and Y extent. Just for the heck of it. Extent of a layer. Let's just do Caswell deer vehicle collision. Let's just try running it again. And it's going to get really ugly really quickly because I specified at 2.72 feet. Really, this is how many 2.72 foot boxes do you have in Caswell County?
So it's gonna be a lot of teeny little grids.
A lot of teeny little grids. Okay. I'm trying to get it to run here. It's not even running yet because it's creating so many. So I'm going to stop that. Yeah. And the other thing that I did do here is I created a good fish net here. And so you can see this fish net that I created just kind of for the entire data set that I created. I also created a bad fish net. Why would something like this be a bad fish net for Caswell County?
You don't have all the data points in the same grid.
Well, I want multiple grids.
Oh, you want multiple? Oh,
Yeah.
I see. It's not enough.
No, not enough.
It's too many of
Yeah.
them. Right? Yeah,
Yeah, not enough.
Okay.
And so that's why we use this formula as guidance here. Use this formula as guidance. Another good thing, long time ago, people, hey, let me use a slightly different formula. 2 times A over N, 2 times A over 2N, 3N, 4N. Let's look at the distribution of data if we change that. That's just some formula someone made up. All right, next thing we've got. Last thing we kind of run into here is what are some of the problems that you see? And if I make this fishnet, if I just make this fishnet blank like this, what are some of the problems with this fishnet? What are some of the problems with this data set?
Well, it goes up over the,
Yeah, it goes up over the top.
yeah,
Okay, and so if I were to run a spatial join right here, I would have one for this, right? 1, 2, 0, 1, 3, 0, 1, 3. But it's not really fair for this one because it's barely within the county. So what do you think we should do? Let's just pick out the quadrants that are entirely within Caswell County. Another thing we could have done is we could have created an extent area around here, create like a buffer to include those. But we don't have near vehicle collisions for Virginia up there, so yeah, you're getting into another state where we don't have the data. So remember what you just did. All right, let me go back. Okay, let me go back. Let me go back. Let me pick out my county here, just for the heck of it. Let me go select by location. Let me find all the Caswell fishnet that is what? Completely within my county. Look what I got there. So now, what do I have here? 36. Does that kind of ring a bell here with what we were looking at here? 37 here. I might have run a slightly different. But look what I have here. Now I got 36 of them here. How do I get rid of all the extras? Can I get rid of all the extras? Watch this.
would you use the switch function?
Exactly. Yeah, I'm gonna do a little switcheroo. And if I really wanted to get cute, I might do something like edit and delete. Oops,
Uh-oh.
what did I
Oh,
do?
wait. Oh, you deleted the county.
I deleted the county too, darn.
Okay.
All right. Oops, all right. So one more time. So fishnet. All right, now this time I'm going to go back to counties, open the attribute table, and I'm going to clear this one. Now I'm going to go back to the fishnet, do what David said before, and do a switch. Click on edit and delete. And it's going to say, are you sure? And yes, of course I'm sure. Don't show me this again. I know what I'm doing.
Okay, so the county was still selected from a
The
while
county
ago.
was still selected when I did the find them all.
Yeah, okay.
All right. So now I want to find which one has the most, which one of these has the most. What do? Spatial join. Watch this. Right mouse click. Joins and relates. I'm going to add a spatial join. I'm going to join this Caswell fishnet with what? I could join it with any of them, right?
Yeah.
But I'll just join it with the Caswell deer collisions. Okay. Now I'm not overly impressed, but what comes up? Now I've got a what? Count. So now I can make a nice pretty map as I'm going through this. Instead of single symbol, graduated colors. What? Not shape length, but join count.
Yeah.
And now I don't even need these deer vehicle collisions anymore. Boom. Look at that.
Oh, that's cool.
That's real cool. Heard someone say this is cool. Listen,
It's brutal.
but I like these maps here because
Yeah.
when you take has anyone taken raster yet? When you take raster or whatever, you're basically creating these rasters. You know, but they've got properties to it above and beyond your typical raster data. Now, someone asks, well, why don't we have this stuff over here? Why? Because, well, when we create the quadrant size based on our little formula, they're not entirely within. So we're going to have some bias. So this is what we call edge effects. So when we look at these, you might have a bunch of 0, 0, 0, 0, 1, 0. Why? Because there's not much of the county, not much of the grid in the county to select it. You also could have used the entire data set, but we talked about, like Fred alluded to before, you know, we're up in Virginia there where we don't have deer vehicle collision. So that top edge is going to be biased or, you know, have bias against it. Now, last thing we're going to do, and when we look at the calculation here, is that we have an observed frequency, a count of 0, a count of 1, a count of 2, a count of 3 in this distribution. So now we were talking about this morning, David, is I got something called the summary. So now what do I have here? I open this up. We go from 6, 6, 5, 5, 4, 4, 4, 3, 3, 3, 3. It looks like 3 is kind of the winner there. A bunch of 2s, a bunch of 1s, and a few 0s. How do I count how many times each of those numbers appears? This is a tough one. We did this with zip codes back in the day. How many times did each zip code appear? What did we do?
Summary.
This is where we run the summarize. Exactly. Perfect. And so now I'm just going to run on this join count. I'm going to run something called the summarize. No, it needs to run a statistic here. I'm just going to do like join count sum. Now what do we have here? So now look what we got here. Join count 0, 1, 2. Yep. Yep, 1's the winner. Now, one thing that I can do is watch this. I'm going to copy this. Now, did everyone see what I did? This slick little thing here. Nothing's selected. I click switch. And now watch. I can copy it right into my Excel spreadsheet here.
Wow. Okay. You truck that. Okay.
Yep.
There you go. I like it.
Now, you notice here, this looks kind of like what we did before. I was probably running the same type of data here. Now, we're going to run a Poisson distribution. This is a sample data set. It's probably similar to what we were looking at here. But do we need this column object ID? No. Nope. Delete. Join count. What's that going to be? We're going to call that thing count, right? What's frequency? Observed frequency. Boom. Just for the heck of it, you know what? I'm going to move these all up a column so everything matches up. What is this? Some fishnet? I don't need that garbage there. Okay, so I got to count. This is what we saw. Fred just said it. Hey, 1's the winner. There was 11 1s. Okay, just like over there. Now next, the tricky one is the Poisson distribution. So all I'm going to do is cut and paste this little, and I'll probably cut and paste the label here. But I'm going to cut and paste this right into here. Now equals Poisson distribution, comma H2. What's H2 going to be? That count.
Oh, it's 0.
Yeah. Do something first. Okay. Now, what is this 2.08108? What is all that stuff? Remember what we had here, that 50 divided by 25.
Okay.
What is the average number of, can you tell me the average number of deer vehicle collisions per square mile in Caswell County? What is the average number of deer vehicle collisions? Oh, actually per quadrant. Sorry about that, per quadrant. Okay, per quadrant. How many deer vehicle, let's go back here. Using this data right here. How many deer vehicle collisions are there? 36 quadrants. 36 quadrants. How do you calculate the total number of deer vehicle collisions? Let's go back to right here. Right here. Let's just do a select by location again. Select by location. Let me find all of the Caswell deer vehicle collisions. Here's what that intersect with what? With Caswell fishnet. Exactly. So we're just picking it. This is my new study area. Let's 80. 80 over 36. What's that equal to? 80 divided, Alexa, what's 80 divided by 36? Yeah. So 80 divided by 36, 2.22222222. Now what's this 2.222? This is the average number of site dots per square. And so you noticed before it was like 2.08. I probably did a slightly different. We might have run this slightly differently. So, but so now equals what? H2, which is the count. 2.2222. What's this false mean? We'll just keep it. That's the Poisson distribution then. If I were to add up all these, so the chances, you have a 10% chance of having 0, a 24% chance of having 1, 26% chance of having 2, 19% chance of having 3, based on an average number of 2.22 points per quadrant. You know we can't have 2.22 points, it's an average.
Right.
You know what an average is from a few weeks ago. So I'm running late, I'm sorry. Not late, but it's running.
Yeah.
We're at 7:17. I get so into it. All right. Now, if we were to add up all these Poisson distributions, what should they add up to? Like it's like rolling dice. What are the chances you have a 1 versus a 2 versus a 3 versus a 4, all the way up to 12? When you added up all those chances on 2 die, what should they all add up to? What are the chances that you get either a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 with 2 die? 100%. Yes, you're going to get one of those at some point in time.
Okay.
Now you don't know which one.
Right, okay.
You know, I got to do combinatorics and math and all that. Now we did Poisson distribution to say, hey, I've got an 11% chance of it getting being 4. I've got a 20% chance of it being 3.
Yeah.
I've got a 26% chance of it being 2. Now, remember the statistics we looked at. Now I will go and add all these up. What do they add up to?
Should equal 1.
0.997.
Okay, okay.
Yeah. So I'll put an 8 right here just for the heck of it. We'll put a 9 right here just for the heck of it. Now what are they starting to add up to here? Add up to
No.
And now the observed is what? Sum of 36. That's how many quadrants here. Last thing we've got here, and we'll make the graph here just for the heck of it. What is the observed? Or what is the expected? Because remember, this average nearest neighbor was based on that expected stuff.
Right.
The chances of it times your, not times distribution, but how many total quadrants do we have? 36. So it's equal to 36 times what? This. Now, and if we were to add them all up, it adds up to now. The one thing about this is, can you have 3.9 quadrants? No. So what is something that we can do? Round it. We have a function called round, comma 0. There we go. And due to some rounding, it goes up to 37 versus 36. I think we had like a 0.49 that got rounded up to 0.50 and
Okay, yeah.
popped it up. But now we can make a graph. This is what we would expect. This is what we saw. Now we want to insert a nice little graph here. And this is what people like to look at. This is what you have on your highlight this. Highlight this, insert, you got a line graph, boom.
The selected one is our blue line, the blue line is the observed frequency.
Yeah, so the blue is the observed. You know that blue kind of goes boom, boom,
Yeah.
boom, boom, where the expected kind of a little bit more, it's like a normal distribution, but you can't go on the other side. You can't have -1, -2, -3 distributions,
Okay.
which is situated about that mean. Now, what's that mean again? That's your mean,
Ah.
about your 2.22. So that 2 point, in theory, it should be right up there. About your mean, but it does kind of go in, because there's chances you might have 5, 6, 7, 8, but there's no chances you're not going to, will have like a -1, -2, -3, 4. So it's not uniform about the mean. So now you got chart. You all know, hopefully most of you know, you can go and change all these things here. So Tim's chart, you can change all the data here. So select data, format axes, all this stuff here. So that you can, the min, the max, the major, text options, fills, all that other good stuff. All right.
Got it.
And then we already did the nearest neighbor analysis for the last question. So if you go to the, excuse me, call boxes.
Yeah.
Right mouse click. Excuse me. Zoom to layer, you go here, uncheck everything. These are all the call boxes on the NCCU campus. Emergency call boxes on the NCCU campus that someone went and collected. One of our students went and collected. You're going to tell me in a short little paragraph, is it clustered, random, or dispersed using what? Average nearest neighbor, which you did at the beginning. Now we actually apply it. In theory, what should it be? I'd like to think it should be dispersed.
Yeah.
Or random. Definitely, hopefully not clustered, right?
Right.
Because that means that.
Yeah.
But these are the emergency call
Yeah.
boxes.
Are most of them by, most
Where
of
you
them
got-
by the residential area? By
Uh,
the residents?
Oh, yeah.
Well, that's.
Some of, yeah, there look like a lot along Boston Street, there's a lot of traffic, foot traffic there.
Right, yeah, and so, for one thing.
Yeah.
But I see it. Very towns would be upset.
Yeah, Marytown's over here, where,
Yeah,
there's a couple on the other side of Bright,
yeah.
Okay.
that way.
Down
Yeah.
there.
All right, well, that's about it for me. I know we ran long, so I get into this stuff. The quadrant analysis is excellent visuals that people like, we got a bunch of points. How can we visualize these points? Because a lot of times you stick 20,000 points up on a map and it's just, you know, I just look at it and, oh, there's a lot of points. So this is one way of making sense of those points. And so all of you joined us online. Thank you. All of us who are watching this later, thank you very much. Let me, Chima, or Tony know of any questions. David's pretty good at this too, so just, you know, ask him for some stuff too as well. So, all right, you all have a good day. Thanks a lot.
And you gonna have to post it up tomorrow anywhere.
Yeah, I'll post it up tomorrow.
What is that?
Yeah.
Because I wanna review.